These are the answers to the AP Chemistry packet that is entitled Unit 2 Summative Assessment Practice. On this slide, you can see Unit 2 at a glance. Unit 2 is entitled Compound Structure and Properties. In this video, I will present practice problems that cover all of the topics in Unit 2. This video should help you to prepare for the Unit 2 summative assessment. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Okay, let's get started. The instructions that you see on this slide are the same instructions that you see on the AP Chemistry free response section. It says, show your work for each question in the space provided. Examples and equations may be included in your responses where appropriate. For calculations, clearly show the method used and the steps involved in arriving at your answers. Now, to be honest, in the Unit 2 summative assessment, there really are no calculations other than adding up the number of valence electrons in a Lewis diagram. So you shouldn't have to worry about significant figures or a lot of calculations on this Unit 2 summative assessment. All right, question 1. Answer the following questions about the polarity of covalent bonds. Part A. Circle the diagram that is the more accurate representation of the polar covalent bond between phosphorus and chlorine. Part B. Justify your choice in Part A in terms of periodic trends and relative values for electronegativity. Here, this information on the slide comes from Topic 2.1, Types of Chemical Bonds, and I've highlighted some of the essential knowledge statements. Electronegativity values for the representative elements increase going from left to right across a period and decrease going down a group. It also mentions that valence electrons shared between atoms of unequal electronegativity constitute a polar covalent bond, and the atom with a higher electronegativity will develop a partial negative charge. So now let's take a look at phosphorus and chlorine. So we can see that phosphorus and chlorine are located in the same period. And remember that electronegativity increases from left to right across a period. So therefore, since chlorine is further to the right, that means that chlorine is more electronegative than phosphorus. So in that bond between phosphorus and chlorine, chlorine will carry a partial negative charge. Again, the justification in Part B is because chlorine is more electronegative than phosphorus. All right, moving on to parts C and D. We have a similar question. Circle the diagram that is the more accurate representation of the polar covalent bond, and then justify your choice based on periodic trends and relative values for electronegativity. Remember that the atom with a higher electronegativity will have a partial negative charge. So the horizontal trend is that electronegativity increases from left to right. The vertical trend is that electronegativity tends to decrease from top to bottom. So oxygen and selenium are in the same group, but since oxygen is further to the top of that column, oxygen is more electronegative than selenium. So now oxygen will carry a partial negative charge. So oxygen being more electronegative than selenium is the justification in Part D. All right, let's take a look at Part E. Circle the bond that has the greatest dipole moment. So in other words, which of these three bonds is the most polar? And then justify your choice in terms of periodic trends and relative values for electronegativity. So on this slide, you can see the essential knowledge statement that says, in single bonds, greater differences in electronegativity lead to greater bond dipoles. So that's what we're looking for. Which of these three bonds has the greatest difference in electronegativity? Now, we don't need to know the actual electronegativity values to answer this question. All we need to do is use our periodic trends, both horizontal and vertical trends, to figure out which of these three bonds has the greatest difference in electronegativity. So I'm going to start with carbon, nitrogen, and oxygen because they are located in the same period. we know that electronegativity increases from left to right, and that carbon being further to the left is less electronegative than nitrogen. So therefore, the difference in electronegativity between carbon and oxygen is greater than the difference in electronegativity between nitrogen and oxygen. That means that the carbon-oxygen bond is more polar and that the nitrogen-oxygen bond is less polar. Now, what about germanium? Well, carbon and germanium are in the same group, and electronegativity decreases from top to bottom. So that means that germanium is less electronegative than carbon. The difference in electronegativity between germanium and oxygen is even greater than the difference in electronegativity between carbon and oxygen. That makes the germanium-oxygen bond even more polar. So the correct answer to this question is the germanium-oxygen bond has the greatest dipole moment. It's the most polar bond because it has the greatest difference in electronegativity between the two atoms. So I circled the germanium-oxygen bond, and then here is my justification. Comparing all four atoms, germanium has the lowest electronegativity value, and oxygen has the highest electronegativity value. The difference in electronegativity between germanium and oxygen is greater than the difference in electronegativity between the atoms in the other two bonds. Part G says to circle the bond that has a dipole moment of 0. If a bond is formed between identical atoms, then the difference in electronegativity would be 0. So the correct answer is the bond between two carbon atoms. All right, let's move on to question 2. The diagram above shows the relationship between potential energy and internuclear distance. The curve for two bromine atoms is indicated by a solid line. So when we see a local minimum in the curve, when we see the potential energy go down to a minimum value, that is the location along the curve of the bond, the stable bond between the atoms. So in part A, use the information in the diagram to estimate the following values. The bond length of the BR-BR bond. So when I look on the x-axis, the position of that minimum in potential energy is approximately halfway between 200 and 250 picometers. So I'm going to estimate it's around 225 picometers for the length of that bromine-bromine bond. Now we also have to estimate the bond energy of the bromine-bromine bond in this question, and it can be a little confusing. When you look on the y-axis, you see both positive and negative values. Remember that when the potential energy is 0, the atoms are so far apart, there's no interaction between them. And as these atoms move closer together, the potential energy decreases until eventually a bond is formed at that minimum in potential energy. Now on the y-axis, that looks like it's approximately negative 200 kilojoules per mole, but we never report a bond energy as a negative value. So what does that negative 200 mean? Well, it's actually the difference between 0 and negative 200. That represents the amount of energy required to break the bond, or if you say it the opposite way, it's the energy released when the bond is formed. But either way, it's going to be 200, approximately 200 kilojoules per mole. That is the energy required to pull the bromine atoms apart and break that bond. All right, let's take a look at part B of this question. Do you predict that the bond length of the chlorine-chlorine bond should be shorter or longer than that of the bromine-bromine bond? Justify your answer in terms of periodic trends. So bond length can be affected by the size of the atoms in the bond, and since chlorine and bromine are in the same family, the same group, and we should know the atomic radius trend. So as we go from top to bottom down a group, atomic radius tends to increase. Now we can make a prediction about the length of the chlorine-chlorine bond. Since the atoms are smaller in size, then the nuclei in that bond are going to be closer together. So the prediction is that the chlorine-chlorine bond should be shorter than the bond length of the bromine-bromine bond. Based on periodic trends in atomic radius, the chlorine atom has a smaller atomic radius than the bromine atom. And since bond length is the distance between the nuclei of the atoms, the chlorine-chlorine bond should be shorter than the bromine-bromine bond. All right, in part C of this question, it says that a student sketched the potential energy curve for two chlorine atoms on the diagram above, as indicated by the dotted line. There is an error with the student sketch. Identify this error and explain how the potential energy curve should be corrected so that it would be a more accurate representation of the bond between two chlorine atoms. So let's take a look along the x-axis. At the local minimum in potential energy for that dotted line, it's around 200 picometers. We have already predicted that the chlorine-chlorine bond should be shorter than the bromine-bromine bond. So the student's sketch of the potential energy curve does in fact show that the chlorine-chlorine bond has a shorter bond length. So this is not the error. Let's take a look along the y-axis. Now, where that minimum is located, it's around 150 kilojoules per mole. So the bond energy that is shown on this graph is 150 kilojoules per mole. That's less than 200 kilojoules per mole, which we got for the bromine-bromine bond. So the student's sketch of the potential energy curve shows that the chlorine-chlorine bond has a lower value for bond energy, as in the bond is easier to break. So this is the error. Here's an essential knowledge statement from topic 2.2, intramolecular force and potential energy. In a covalent bond, the bond length is influenced by both the size of the atom's core and the bond order, that is, single, double, and triple. Bonds with a higher order are shorter and have larger bond energies. Now, we are not in this question comparing a single bond with a double bond or a triple bond, but a shorter bond should be more difficult to break. So that's the problem here. If a shorter bond tends to be more difficult to break, then the chlorine-chlorine bond, which is shorter than the bromine-bromine bond, should have a higher bond energy. So in the student's sketch, that local minimum in potential energy should be further down to indicate that the bond energy of Cl-Cl is greater than the bond energy of Br-Br. So if I were to redraw that curve, it would look something like this, showing that it's a shorter bond but has a higher bond energy. So this idea that when two atoms in a chemical bond are closer to each other, then more energy is required to break the bond between them. That is definitely true with covalent bonding, but it's also true in ionic bonding. So with ionic bonds, and when we talk about lattice energy and Coulomb's law, we will see that when the distance between the ions in the crystal lattice is smaller, then more energy is required to pull the ions apart from each other. If you wanted to see the actual value for the bond length and the bond energy comparing chlorine and bromine, here is the data. So you can see that for bond length, for chlorine, it's around 200 picometers, and for bromine, it's around 228. So again, the chlorine bond is shorter. And then for bond energy, it's 243 kilojoules per mole for chlorine compared to 193 for bromine. So that chlorine-chlorine bond does require more energy to break that bond. All right, let's move on to question 3. We are given a data table with appearance and melting point. Part A, circle the chemical formula that is more likely to have the properties listed in the table above. And our choices are CaCl2, so calcium chloride, and SCl2, sulfur dichloride. Part B, justify your choice in Part A in terms of the type of bonding present in each substance. So one of the things you should notice right away in comparing these two chemical formulas is that calcium chloride contains a metal and a nonmetal, whereas sulfur dichloride contains two nonmetals. So we can already tell that calcium chloride is likely to be an ionic substance, again, metal and nonmetal, whereas sulfur dichloride would tend to be a covalent or molecular substance because it contains two nonmetals. In an earlier video, when I was talking about topic 2.1, I showed this slide, which does a comparison between an ionic substance and a covalent substance. So an ionic substance consists of positive and negative ions, and a covalent or molecular substance consists of individual molecules. With respect to the physical properties, for an ionic substance, it is a solid at room temperature. It tends to be a hard, brittle solid with a relatively high melting point. It does not conduct electricity as a solid, but it does conduct electricity when either melted or dissolved in water. A covalent substance can exist as either a solid or a liquid or a gas at room temperature, and if it is a solid, it is a soft solid with a relatively low melting point. And a covalent or a molecular substance does not conduct electricity whether it is a solid or melted or dissolved in water. Now, back to the physical properties of this particular substance in question 3. What we know is that it's a liquid at room temperature and it has a very low melting point. In fact, the melting point is negative 121 degrees Celsius. So this is unlikely to be an ionic substance. It is more likely to be a covalent substance. So I'm going to circle sulfur dichloride because it contains 2 nonmetals, so it would tend to be a covalent substance. All right, here is my justification in part B. Calcium chloride contains a metal, calcium, and a nonmetal, chlorine. It is an ionic substance. An ionic substance tends to be a hard, brittle solid at room temperature with a relatively high melting point. This particular substance is a liquid with a very low melting point. It is more likely to have covalent bonding, and sulfur dichloride, SCl2, contains 2 nonmetals, so it's a covalent or molecular substance. All right, now let's take a look at question 4. The Lewis diagram for C2H6 is shown above. Part A, draw the correct Lewis diagram for C2H2. So the first thing to do is to count the total number of valence electrons. That would be 4 for carbon times 2 plus 1 for hydrogen times 2. So we have 10 valence electrons for the C2H2 molecule. Now, as far as the skeleton and how to connect the atoms, let's connect the 2 carbon atoms, and let's put 1 hydrogen on either end of the molecule like this. So now we've used up 6 valence electrons in drawing these 3 single bonds. Now with a lone pair, this would be 8, 10. So unfortunately, with only 10 valence electrons, there's not enough electrons to put lone pairs on both carbon atoms. Let's try making a double bond by moving this pair of electrons in the center. So making a double bond still doesn't solve the problem that the carbon on the right does not have access to a complete octet, so we have to make a triple bond. And now this structure is complete. We have 10 valence electrons, we have a single bond between the carbon and the hydrogens, and we have a triple bond between the carbon atoms. Part B, the bond energy for the carbon-carbon bond in C2H6, which as we can see is a single bond, is approximately 350 kilojoules per mole. Do you predict that the bond energy of the carbon-carbon bond in C2H2, which we just discovered was a triple bond, should be less than or greater than 350 kilojoules per mole? Justify your answer. So when I was teaching about topic 2.2, it says that in a covalent bond, the bond length is influenced by both the size of the atom's core and the bond order, single, double, triple. Bonds with a higher order are shorter and have larger bond energies, so it should take more energy to break a triple bond than it does to break a single bond. So the prediction is that the bond energy of the carbon-carbon bond in C2H2 should be greater than 350 kilojoules per mole. Again, a triple bond has a higher bond order, so that is a stronger bond and requires more energy to break. All right, let's take a look at question 5. Now, earlier in this video, at the end of question 2, when I was looking at that potential energy curve, we were talking about the concept that a shorter bond requires more energy to break. And I had mentioned that lattice energy is very similar to that concept, where if the ions are closer to each other in the crystal lattice, then more energy is required to pull them apart. So here we have a great example of lattice energy and Coulomb's law. Question 5. The energy required to separate the ions in the crystal lattice of an ionic solid into individual gaseous ions is known as the lattice energy. The lattice energy of sodium chloride is equal to 788 kilojoules per mole. Now, in this table, we have two other compounds. They're both ionic compounds. One of them is potassium chloride, and the other is magnesium chloride. So for each of these compounds, we're going to have to make a prediction if the lattice energy should be lower than or higher than 788 kilojoules per mole, and we'll have to justify our prediction based on periodic properties and Coulomb's law. So earlier in a previous video, we were talking about Coulomb's law and lattice energy. So take a look at this side-by-side comparison. You can see two particulate models of an ionic compound in which the ions have approximately the same size in both compounds, but one of them, the charges are +1, -1. The other, the charges are +2 and -2. So a higher lattice energy for that compound on the right is because of the greater charge magnitude, stronger attractive forces between the ions. That is the numerator, Q1 and Q2, in Coulomb's law, the magnitude of the charges on the ions. Now, with respect to the distance between the ions and the crystal lattice, smaller ions are going to be closer to each other, so a smaller distance between them, and then larger ions are going to be farther apart. The smaller distance would be a greater attraction between the ions. So the magnitude of the lattice energy of an ionic compound tends to increase as the magnitude of the charges on the ions increases and as the distance between the ions in the crystal lattice decreases. Now, let's take a look at our examples in this particular question. So, let's compare sodium and potassium because that's the only difference between sodium chloride and potassium chloride. They have the same magnitude of charge, but as you know, atomic radius increases from top to bottom down a group. So potassium, the ion, is larger in size than sodium, the ion. So there's a sodium ion, and there's a potassium ion, which is larger. So the distance between the ions in potassium chloride is greater than the distance between the ions in sodium chloride. Now let's connect that to Coulomb's law. The lattice energy of KCl should be lower than 788 kilojoules per mole. Potassium has a larger ionic radius than sodium. The distance between the ions in KCl is greater than the distance between the ions in NaCl. Therefore, there is a weaker attraction between the ions in KCl than there is in NaCl. So in part A, it was about the distance between the ions in the crystal lattice. Now let's take a look at part B. In part B, we are comparing the lattice energy of magnesium chloride with the lattice energy of sodium chloride. So sodium and magnesium are in the same period, and as we go from left to right across a period, the atomic radius decreases. So magnesium, the ion, is actually a little bit smaller in size than sodium, the ion. But I think more importantly, the magnitude of the charge on magnesium is twice as much as the magnitude of charge for sodium. So here's my model for sodium chloride, so +1 and -1. Now here's my model for magnesium chloride, and so I'm showing that the charge on the magnesium ion is greater, the magnitude of charge is greater for magnesium than sodium. That's going to be a greater attraction between the ions based on the numerator of Coulomb's law. So the lattice energy of magnesium chloride should be higher than 788 kilojoules per mole. Magnesium, Mg2+, has a greater charge magnitude than sodium, Na+. That would lead to a stronger attraction between the ions. Again, that's the numerator of Coulomb's law. So a stronger attraction, greater lattice energy, comparing magnesium chloride to sodium chloride. All right, let's take a look at question 6. In the space below, complete the Lewis electron dot diagram for the S2Cl2 molecule by drawing in all of the bonding and non-bonding electron pairs. The first step is to count the total number of valence electrons. So for this molecule, it's going to be 6 for sulfur times 2 plus 7 for chlorine times 2. That's a total of 26 valence electrons. We'll start off with single bonds to connect the atoms. So I've used up 6 electrons in drawing these 3 single bonds, and now we'll satisfy the octets around the terminal atoms using lone pairs of electrons. So after 6 comes 8, 10, 12, and then we'll keep going on the other side of the molecule, 14, 16, 18. So I still have more electrons I can use as lone pairs, 20, 22, 24, and 26. Now, with 26 valence electrons, I was able to satisfy the octet of all of these atoms without using any multiple bonds. So that Lewis electron dot diagram is now complete. Part A says, what is the approximate value of the chlorine-sulfur-sulfur bond angle in the S2Cl2 molecule that you drew above? Now, a Lewis diagram doesn't necessarily show you the actual molecular geometry of the molecule. So just because all 4 of these atoms are written in a straight line does not mean that the bond angle in this molecule is 180 degrees. So how do we figure out the bond angle? Count the total number of electron domains. So we're focusing on the sulfur atom. This is a chlorine-sulfur-sulfur bond angle. And so that sulfur atom has a total of 4 electron domains. There are 2 bonding domains, and there are 2 lone pairs or non-bonding domains. In the video for topic 2.7, which includes hybridization, you can see that the hybridization around the central atom is related to the number of electron domains around that central atom. And so we're looking at 4 electron domains around the sulfur atom in this particular molecule. That means that we can learn the bond angle, which is approximately 109.5 degrees, and the hybridization, which in this case would be sp3. So the bond angle based on 4 electron domains is 109.5 degrees approximately, and the hybridization based on 4 electron domains is sp3. In question 7, we have to draw the Lewis diagram for a polyatomic ion as opposed to a molecule. In the space below, complete the Lewis electron dot diagram for the NO2- ion by drawing in all of the bonding and non-bonding electron pairs. Let's count the total number of valence electrons for this ion. It's going to be 5 for nitrogen plus 6 for oxygen times 2. That would be 17. And then we get to add 1 more for the negative charge, so 18 valence electrons. First, let's connect the atoms with single bonds. So I've used up 4 electrons in drawing 2 single bonds. And now let's satisfy the octets of the terminal atoms and see how many electrons we have. So this would be 4 right now. 6, 8, 10, 12, 14, 16, 18. So I've just run out of electrons, and I don't have enough electrons to satisfy the octet of that central nitrogen atom. So I'm going to have to make a double bond on one side of this polyatomic ion. So I'll move a pair of electrons from the oxygen to make a double bond, and now that structure is complete in that each atom has an octet. Part A. What is the approximate value of the ONO bond angle in this particular ion? So we're going to do the same thing we did in question 6, which is to count the total number of electron domains. So for this central atom, a bonding domain can be a single, double, or triple bond. So we have 2 bonding domains, but then we also have a lone pair or a non-bonding domain. That is a total of 3 electron domains. That would correspond to sp2 hybridization, and we would expect a bond angle of approximately 120 degrees. So approximately 120 degrees for the bond angle, and sp2 for the hybridization, because there are 3 electron domains around the central atom. Now we come to part C. Do you predict that the nitrogen-oxygen bonds in this NO2- ion should have the same length or have different lengths? Justify your answer. You may remember in topic 2.6, which includes resonance and formal charge, there is more than one possible resonance structure. In this case, we have a double bond that could have been drawn either on the left or on the right. This is very similar to the ozone molecule, O3, or the sulfur dioxide molecule, SO2. They also have 18 valence electrons. So the actual structure of this ion is a hybrid or an average of these two resonance structures. So the answer to part C is that the two nitrogen-oxygen bonds in this NO2 minus ion actually have the same length. So the actual structure of this ion is a hybrid or an average of these two resonance structures where the electrons are delocalized. You may recall that a single bond has a bond order of 1 and a double bond has a bond order of 2. In this particular polyatomic ion, the bond order of the nitrogen-oxygen bonds is actually 1.5. So it's an average of a single and a double bond. So these two resonance structures are both incomplete and inaccurate, but together the average of these two structures is what the polyatomic ion looks like. All right, let's move on to question 8. Question 8 says, a particle diagram is shown above that is intended to represent a portion of the crystal lattice in lithium fluoride, LiF. Identify an error that is shown in this particle diagram. Explain how the particle diagram should be corrected so that it would be a more accurate representation of LiF. So lithium fluoride is an ionic compound that contains a metal and a nonmetal. And what we are seeing in this particle diagram is the charge on lithium is +1, and that is correct. The charge on the fluoride ion is -1. That is also correct. I see an alternating pattern of positive and negative ions in this three-dimensional matrix or crystal lattice. So that looks good. The problem is the relative size of these ions. Now, considering the number of electrons for each ion, Li plus should have 2 electrons. F minus should have 10 electrons. So the lithium ion is actually smaller in size than the fluoride ion. So to change that part of the particle diagram, that is how the particle diagram should be corrected. Lithium plus should be smaller than fluoride, F minus. All right, this is question 9. The table above provides some information about two types of steel, both of which are alloys of iron and carbon. Part A. Should steel be classified as a substitutional alloy or as an interstitial alloy? Justify your answer in terms of the relative sizes of the atoms of iron and carbon. So back when I was teaching topic 2.4 in this unit, which has to do with alloys, I taught you that a substitutional alloy is formed between two different atoms whose atomic radius values are similar to each other. On the other hand, an interstitial alloy is formed between two atoms in which the atomic radius of one atom is much smaller than that of the other, and the smaller atoms can fit in the empty spaces in between the larger atoms. By the way, it also says on this slide that one example of an interstitial alloy is steel, so that kind of gives it away. But let's take a look at the periodic table. Carbon is in period 2, whereas iron is in period 4. So we expect that the iron atom should be larger in size than the carbon atom. Here's some actual data for atomic radius. And so carbon has a value of approximately 77 picometers, and compare that with iron, which is around 125 picometers. So the fact that steel is classified as an interstitial alloy can be explained because the atomic radius of carbon is smaller than the atomic radius of iron. So on this slide it says that an interstitial alloy is often stronger than the pure metal because the presence of the smaller atoms in the empty spaces makes it more difficult for the atoms of the alloy to move and slide past each other. So that's our explanation in part B. Explain why high carbon steel, which again contains a higher percentage of carbon, is more rigid than low carbon steel. So the carbon atoms fit in the spaces in between the iron atoms, and this makes it more difficult for the iron atoms to slide past one another. All right, let's take a look at question 10. Three possible Lewis diagrams for the thiocyanate ion, NCS-, are shown in the table below. Part A. Assign formal charges to each atom in each Lewis diagram. Remember that the formula for calculating the formal charge is valence electrons minus the total number of dots and bonds. So let's start with Lewis diagram number 1, and we'll begin with the nitrogen atom. Nitrogen has 5 valence electrons. I see 4 dots and 2 bonds. That would be 5 minus 6, so a formal charge of -1. Carbon has 4 valence electrons, and I see 4 bonds, so 4 minus 4 is 0. Sulfur has 6 valence electrons, and I see 4 dots and 2 bonds, so 6 minus 6 is 0. Moving on to Lewis diagram number 2. Nitrogen has 5 valence electrons. I see 2 dots and 3 bonds. That's 5 minus 5, so that's 0. Carbon has 4 valence electrons, and I see 4 bonds, so 4 minus 4 is 0. Sulfur has 6 valence electrons, and I see 6 dots and 1 bond, so 6 minus 7 is -1. And now moving on to Lewis diagram number 3, nitrogen has 5 valence electrons, and I see 6 dots and 1 bond. That would be 5 minus 7, so -2. Carbon has 4 valence electrons, and I see 4 bonds, so 4 minus 4 is 0. Sulfur has 6 valence electrons, and I see 2 dots and 3 bonds, so 6 minus 5 is +1. So of the 3 Lewis diagrams, we're trying to get formal charges as close to 0 as possible. I would say that Lewis diagram number 3 is probably the worst. We're trying to get formal charges as close to 0 as possible, and if there is a negative formal charge, we want the dominant Lewis structure, or the one that is the most favored, is the one in which the negative formal charge is assigned to the more electronegative atom. So again, Lewis structure number 3 is probably the least favorable because of that higher magnitude of formal charge. So a -2 formal charge is not preferred. Now, of the 2 that remain, they both have formal charges of 0, 0, and -1. Let's take a look at the electronegativity values for these 3 elements. So we can see that given the information in the table, nitrogen is the most electronegative element in this set of atoms. So which Lewis diagram is the most preferred if we can put that negative formal charge on the most electronegative atom? That would be most preferred. So Lewis diagram number 1 is the most favorable because it places the negative formal charge on the most electronegative atom, in this case, nitrogen. All right, it's time to take a look at question 11. Identify the total number of sigma bonds and pi bonds present in the molecule represented by the Lewis diagram shown below. Remember that a single bond represents 1 sigma bond, a double bond represents 1 sigma bond and 1 pi bond, and a triple bond represents 1 sigma bond and 2 pi bonds. I'll start by counting all of the sigma bonds in this Lewis structure. So I see 1, 2, 3, 4, 5 single bonds. Now I do see a double bond, but that's 1 sigma and 1 pi, so I'll count one of those dashes. Then there's another single bond. Now I have a triple bond, but that would be 1 sigma and 2 pi, so I'm going to count one of those dashes. So there is a total of 10 sigma bonds that I have counted so far. Now for the pi bonds, I'll use a different color for that. I see 1 pi bond there in the double bond, and I see 2 pi bonds as part of the triple bond. So a total of 3 pi bonds. And again, you can take a look at the video for topic 2.7 if you want to see another example of me counting sigma and pi bonds in a Lewis diagram. All right, let's take a look at question 12. Fill in the missing information in the table below. So we have 5 different molecules. We have to determine the molecular shape and decide if it's polar or nonpolar. Let's start with ClF3. That's 7 valence electrons for chlorine, 7 for fluorine, times 3. That would be 28 valence electrons. Now, 28 is not a multiple of 8, so we're going to have a central atom, chlorine, with 3 fluorine atoms. Each of those terminal fluorine atoms will have a complete octet. But since 3 times 8 is 24, then What do I do with these extra 4 electrons after I've satisfied all of the octets of the terminal atoms? Well, you just place those extra electrons on the central atom. So this is what the Lewis diagram of ClF3 looks like. And if you were to build this type of molecule in the PhET simulation on molecular shapes, you'd realize that we have 3 bonding domains, 2 non-bonding domains or lone pairs, and that's going to correspond to a molecular shape that we call T-shaped. Now let's draw the dipoles between the chlorine and the fluorine and see if they are symmetrically arranged and if they cancel each other out or not. So the way these dipoles are arranged, they're not symmetrical around the entire molecule. They're pointed to one side and they're not going to cancel each other out. This is not trigonoplanar. If it were, then they would cancel each other out. This is T-shaped. So because they're asymmetrically arranged and they're not going to cancel each other out, this is a polar molecule. Now on to SF4, sulfur tetrafluoride, 6 for sulfur, plus 7 for fluorine, times 4. That would be a total of 34 valence electrons. Again, not a multiple of 8. I'm going to have 4 octets, so 4 times 8 is 32. And then I'll have an extra pair of electrons. And where do I put this extra pair of electrons? Right there on the central atom. And if you build this molecule with the PhET simulation for molecular shape, you can see 4 bonding domains and 1 non-bonding domain, the lone pair. And this particular shape is called seesaw. The dipoles are not symmetrically arranged around the entire molecule. They're sort of pointed to one side there, but there's not an even distribution of these dipoles. So because of the asymmetry of this shape, this is a polar molecule because the dipoles are not all going to balance and cancel each other out. Now we have xenon tetrafluoride. That's 8 for xenon plus 7 times 4 for the fluorines. That's going to be 36. Again, not a multiple of 8. 4 times 8 is 32. I'm still going to have 4 more extra electrons on the central atom. So when you have 4 bonding domains and 2 non-bonding domains, the shape that we get is called square planar. But because these 4 fluorine atoms are all 90 degrees apart and evenly distributed in this plane, they would cancel each other out because of that symmetry. This is a non-polar molecule. All right, our next example is CF4, carbon tetrafluoride. That's 32 electrons because it's 4 plus 7 times 4. So with 32 electrons, there's not going to be any extra lone pairs on the central atom. It's just simply 4 octets. 4 times 8 is 32. The shape is tetrahedral. Everything is balanced, symmetrical. All the dipoles cancel out. This is a non-polar molecule because of the symmetry of that tetrahedral shape, and all 4 atoms are the same. Now, what happens if I change this molecule so that 2 of the fluorines are replaced with hydrogen atoms? Now we have CH2F2. That's going to be 4 plus 1 times 2 plus 7 times 2. That's 20 valence electrons. Here's my Lewis diagram. It's not symmetrical like it was before with 4 fluorine atoms. Still tetrahedral, but now it's not going to be balanced in the same way. So when you have a tetrahedral geometry, but all 4 atoms on the corners of that tetrahedron are not the same, then this now becomes a polar molecule. So remember, if you have a tetrahedral molecule, it will only be classified as nonpolar if all 4 of those terminal atoms are identical. 4 fluorines, 4 hydrogens, 4 chlorines. But if you have 2 of one type of element and 2 of another, or if you have 3 of one type of element and 1 of another, that is asymmetry that messes up the balance, and that would become a polar molecule. All right, let's take a look at question 13. We have BF3, boron trifluoride, and we have NF3, nitrogen trifluoride. For each of these molecules, we have to draw the Lewis diagram, identify the molecular shape, identify the approximate bond angle, the hybridization of the central atom, and then classify it as polar or nonpolar. Let's start with BF3. 3 for boron, 7 for fluorine times 3, that's 24 valence electrons. BF3 is going to have 3 single bonds, and it can be shown with formal charges that instead of making a double bond between the boron and the fluorine to satisfy the octet, we leave it as 3 singles because it would put a positive formal charge on the fluorine if we make a double bond. So boron is an exception to the octet rule in that it has less than an octet around the central atom. Hopefully you can see with 3 single bonds, it's going to be trigonal planar. Therefore, the approximate bond angle for trigonal planar is 120 degrees. 3 electron domains would be sp2. And everything is nice and symmetrical and balanced in this molecule, so it is nonpolar. All the dipoles would cancel each other out. Now, with NF3, it's very similar in that we have 3 fluorines, but this is not 24 valence electrons. 5 plus 7 times 3 is actually 26. So we're going to have an extra pair of electrons on the central atom. That means it will not be trigonal planar, but rather trigonal pyramidal. Because of that extra lone pair on the central atom, that causes the shape to be trigonal pyramidal. Now the bond angle is approximately 109.5 for a trigonal pyramidal geometry. We have 4 electron domains, so 3 bonding and 1 non-bonding domain. That's going to be not sp2, but rather sp3, because there is a total of 4 electron domains. And trigonal pyramidal geometry is not symmetrically arranged in 3-dimensional space like trigonal planar is. Those dipoles are not going to cancel each other out. So because of that asymmetry, this is a polar molecule. All right, on to question 14. Comparing the Lewis structures of CH4 and NH3, each Lewis structure contains a central atom with a total of 4 electron domains. It is observed from experimental evidence that the bond angle in NH3 is slightly less than the bond angle in CH4. Give an explanation for this observation. So in an earlier video talking about bond angles, I'd mentioned the following. A bonding pair of electrons is attracted by the nuclei of 2 atoms. Therefore, the bonding electrons are likely to be located in the space between the 2 atoms that share them. However, a non-bonding pair or a lone pair of electrons can spread out more, occupying more space than a bonding pair. And as a result, a lone pair tends to exert greater repulsive forces on the nearby bonding pairs, reducing the bond angle slightly. So compare CH4, which would be 4 bonding domains, with NH3, which is 3 bonding domains and a lone pair or a non-bonding pair of electrons. So that central atom in NH3 has a lone pair of electrons which can spread out more, occupying more space than a bonding pair, exerting greater repulsive forces on the nearby bonding pairs, reducing the bond angle in NH3 slightly. All right, well, question 14 was the last question on the Unit 2 summative assessment practice. So I hope that these answers and explanations were helpful. Thanks for watching and good luck studying for your Unit 2 summative assessment.